Welcome to our fourth lectures of NPTEL on flexible AC transmission system fax devices. Today we shall discuss about the PWM. PWM technique will be covered in detail and we shall see that what are the different kind of PWM technique. So we have already seen or studied in power electronics that 180 degree mode of conduction and the 120 degree mode of conductions of this inverter, and generally these are the actually salient point of it. These are called actually 3-phase 6 steps inverter, and its control is very simple and it can be put into this application with the SCS, but it also contains lower order harmonics. That is one of the disadvantage of this kind of converter, and that leads to the higher current distortion. PWM on the other hand, PWM inverter on the other hand can actually offer better harmonic, better THD, because here what happened here, it actually voltage harmonic almost even same, but current harmonic actually been reduced, because most of the cases in our fax applications and the drive system, our system itself is a low pass filter, and ultimately it will shift to the spectrum to the 20 times or 30 times depending on the ratio of the carrier wave and the control wave that we will see later, and thus THD content will, current THD content will be very lower compared to this square wave inverter, and it can also scale up and scale down the voltage in a linear region. That is one of the advantage of it. PWM also provide that is linear control of the output as desired by the reference. That is what actually was been mentioned. Now we shall first discuss, this is our presentation layout today. We shall discuss sinusoidal PWM, that is most commonly used. There are another different kind of PWM also, that is trapezoidal PWM and other. Thereafter we shall see that actually selective harmonic eliminations, and thereafter we shall discuss space vector modulation and instantaneous current control by the PWM. It will have application because in our fax devices mostly we use voltage source inverter in current control mode. So this has its own actually advantage. Thereafter we shall discuss this advantage of the hysteresis current mode control PWM, so which is very simple to implement. Now most common, as told in previous case, most common approach is a sinusoidal PWM. Here what happened in this case, sine wave, that is mostly the control wave or the modulating wave, it will be actually compared with the triangle wave, and it will accordingly actually reference will be generated. We can see the next slide. And so now question is, how can a sinusoidal or other signal, it can be trapezoidal or any other signals, in case of the shunt active power filter, the reference is actually little picky and different kind of actually combinations of harmonics, but each of the cases whatever may be the input signal can be identified with a low distortion. This is a challenge, and answer is the switching can be controlled in a smart way, so that FFT of the V-load has a strong fundamental component plus high frequency switching harmonic that can be easily filtered out by the system or by a small low pass filter. So this is basically the PWM signals, and where actually its volt area will match. Actually it is not that we are applying a sine, but sinusoidal volt area and this actually PWM volt area will match each other. We will come later, this is called a actually unipolar PWM, and this is one of the advantage. You can see that since this area in the central portion is more, and thus we can see that it will be more squarer at the center, and it will be actually it will have a less it will have a narrow fringes in the end at the beginning of the cycle. So this is actually the single phase and the 3-phase voltage source inverter, and we take a simple bridge topology of the 2-level inverter. Subsequent classes we shall discuss about the PWM applicable for the 3-level inverter and its applications. So, let us now see that what is the functionality or principle of operation of the inverter. Please go back this circuit and see that what are the switches been mentioned. It is a half bridge combinations, and in half bridge combinations average voltage applied across is VDC by 2, and so this is the upper switch and this is the lower switch. So, we see that, and our switch is marked as a T plus and the lower switch is marked as a T minus. Now, see that what is the logic? When the control signal VAO actually is greater than the triangle signal Vt, then upper switch will be on and lower switch will be off, thus you will get a voltage of half VDC. Similarly, when actually reverse condition is satisfied, that is triangular wave is greater than the modulating signal, and then upper switch will be off and the lower switch will be on, and you will get a signals of it, and thus you will getting this kind of PWM waveform which amplitude actually varies plus minus VDC. Now, one of the beauty of it that this is a line voltage where you subtract VAV, and this is one of the phase voltage. So, you see that line voltage may have a huge amount of the harmonic content, and also sometimes it will have a actually bipolar in nature, but you will find that actually line voltage is unipolar and harmonic content is considerably low. See, now these are the few basics of the PWM. We refer actually the triangular wave frequency or the carrier frequency, and it will be referred as a FC, and same way the control frequency will be referred as F. So, the amplitude of the modulation is a ratio of actually peak amplitude of the control signal Vp and the peak amplitude of the triangular signal Vt, that is called the amplitude modulation. Same way there will be another term that will be actually frequency modulation, that will be MF, that will be given by actually the ratio of the Fc by F, where Fc is the carrier of the triangular wave frequency and F is the control signals frequency. Now, again let us go back to the same circuit and we shall discuss about the bipolar PWM, and it is the simplest PWM of itself. And the output voltage of the leg A is generally a comparison between V control and the Vt or V try, and leg B is the negative of the leg A. Now, this is actually the bridge configuration. Now, what happened when the pair of switch are actually Ta minus Tb and plus Tb and minus Ta. When the leg B is negative of leg A, then what happen you will get actually the output voltage VOB, and that is given by 2, that is actually the minus 2 VO, and thus actually the fundamental voltage which is available, it is m times of the DC-link voltage in case of the full bridge configuration, and half bridge configuration it will be half of it, and provided that modulation index is less than 1. We shall go little we will go to the little discussions of it, and when we have a fundamental waveform, if we do the Fourier series analysis and we can find its fundamental voltage, that is it is 4 by pi into the DC-link voltage. So, for this reason this will be the fundamental voltage for this actually modulating index while more than 1, and for half bridge it will be actually 2 Vm by pi, because actually the DC-link voltage will be half this DC-link voltage of the bridge converter. Now, we will continue with the actually PWM. One of the advantages is that it requires only one control signal, and it can be controlled as said earlier. We can see that when sine or the V control is greater than V try then the output of the controller will be higher. But problem is that there is one of the biggest disadvantage of this bipolar PWM is that harmonic content. For this reason, you take this region into the account. Here you can see, or this region into the account. You can see you are applying the voltage of minus VDC or VDC by 2 depending on the topology, and where you got a huge instantaneous voltage error, and generally this instantaneous voltage error is filled by the harmonics. So, harmonic content will be moreover, and it will find it out, its dominant when we will discuss about its harmonic spectrum, we will find out that it is shifted by the ratio Fm, but little later we will discuss about unipolar PWM, then we will find its applications and advantages. So, this is the harmonic spectrum, this is a fundamental, and then it will be shifted by the MF, where MF is a ratio of the triangular wave by the triangular wave or the carrier wave by the control wave. So, this is for basically for modulation index in a linear region of 0.8 and value of the MF as 15, and we can choose a MF in such a way that should be the odd number, then we will find that odd harmonic only survives, and in that way we can actually eliminate this even harmonic, and then again it will be available in 2 MF and subsequently 3 MF like that. And since it is actually very high frequency lower order, so it can be easily eliminated by a small low pass filter, or the system being actually power system or the drives all comes inherently is basically inductive, and thus it will eliminate this high frequency very easily. Now, let us go back again little bit, and now we will discuss about actually the 2 level inverter and for the bipolar operation, sorry unipolar operation. In this case actually load voltage again will be VAB, and we have already discussed what is the principal operation, and this is the principal operation when actually we see that when diode conducts, when switches conducts and other thing. Now, let us come to this actually unipolar PWM operation. In this case actually you require V sin omega t and the minus V sin omega t, and you require actually this inverted signal also. So, that is basically you require little bit more complex circuit, but it is not very complex. You can generate the negative of the voltage by simply actually op amp in a inverting mode. Now, we want to actually amplify the V count whatever actually control signal according to the amplitude, and see the advantage of it over the previously discussed bipolar PWM. And in this case we require to mention that actually the triangle wave its frequency should be actually around 30 times more. Generally there is IEEE standard said that you should have a 48 cuts in a cycle, that means the frequency should be around 24 times more. So, as discussed previously, MA is a peak angular signal ratio by the peak angle of the wave ratio. So, here what we can find, the implementation rules are same of it. So, when actually V count is actually more than V try, upper switch actually A plus opens and the A minus actually also opens, thus you are getting a voltage for the full bridge configuration VDC. Same way, when other condition is satisfied, means in this region actually V count is less than V try, then what happen actually upper switch actually is open, the A1 actually opens and the A minus switches closes. So, you get a voltage 0, not minus VDC. So, similarly, when minus count is greater than try, then it closes the plus actually switches upper switches of the phase B, and it opens actually the negative switch of the phase B. Thus, you are getting basically again plus VDC. Similarly, again you can get actually if it is minus V count is basically less than V try, then plus V closes and minus V closes. So, plus V opens and minus V closes, and so you get actually again the 0 voltage. So, you can also here you can generate 0 voltage. So, for this reason what happened, let us see that this is a configuration of it. Actually the red or the purple line shows when capital A is closes. So, when this actually condition is satisfied, what happen, capital A is closes and minus A actually lower switch of the phase A opens, and so you are getting actually the voltage of VDC. Otherwise what will happen, actually you will close minus A and plus A will open and you will get a 0 voltage, not minus VDC, mind it. Similarly, in lower half basically plus B closes and plus B closed and minus B open, you get actually VB equal to VDC, and else you get VB equal to 0. Since you want to get a pole voltage of B, so thus actually it will become unipolar. So, ultimately this will be subtracted from it, because this is basically A voltage and this is the B voltage, and ultimately this will get subtracted, and so you get actually the resultant waveform something like this. And what is the advantage of it? Advantage of it that actually its instantaneous voltage error is half. Since let us consider that this is actually the sine wave where actually both area graph has matched, and so for this reason you can find that voltage error here actually will be actually only the half of the error voltage than compared to the bipolar. And another advantage is that it eliminates huge amount of harmonic. Why? Because it forms a note in this actually the 0 potting. So, in that way actually many undesirable harmonic is been actually truncated, and moreover instead of shifting this dominating frequency after fundamental to F, it will actually transfer to it to F. So, you require very smaller inductor or the low pass filter to eliminate this high frequency ripples. So, this is actually the PWM waveform, and that will be generated, and I am assuming that actually the value of MA as 0.5, that means it is in a linear region. Thereafter, what happens if we go to the M greater than 1, it is same as discussed into the bipolar PWM. Here value of this will be actually, here it will lead to the saturation, only will have a, it will have a crossing at the very beginning. Thereafter actually you get a almost a square kind of waveform, and it is called overmodulation. And generally this M also sees some kind of hysteresis graph, which we have been all have studied actually in BH curve. So, what happen till 0 to 1 it is a linear region, and in terms of the RMS value you will get the value of M is something like this √2 B RMS by VDC. We know that for the square wave the fundamental value is 4 V by pi. So, this will be the saturation value which you can have from this thing, but you may actually having a higher fundamental value, but you will be sacrificing actually higher contamination of the THD. That is one of the disadvantage of this kind of when you go to the overmodulation. Otherwise, in this region you can control the magnitude of this output voltage by simply controlling the modulating index. Now, this is actually this table shows how relative strength of the different kind of harmonics. You can see that at fundamental, so if you it will be increasing linearly, but higher order harmonics will be actually changing first of all linearly, thereafter actually at the 1 it will reduce. Same pattern will be followed actually here you can see that it is actually increasing, thereafter it is strictly increasing. So, you have to keep in mind while designing filter what will be the relative strength of the different kind of harmonic in different frequency. Accordingly, actually we require to take a call to design the harmonic. So, what are the takeaway or advantages of the PWM? PWM is very simple to implement. High frequency normal leakage inductance of the machine will effectively filter out, and thus inverter current, or in case of the STATCOM or in case of the fax applications, generally we connect the pole of the inverter with that is called, this point is called point of common coupling with an inductor with the inverter. So, since there is an instantaneous difference between the actually the value of the phase voltage value or the line voltage value and the pole of the inverter. So, for this reason we put an inductor. Ultimately, this inductor itself also will filter out the high frequency harmonics. And generally what happen, actually there is a second point, FC leads to higher switching losses, and also we require to choose a switch of the higher frequency rating. So, but it actually lowers the harmonic losses since amount of the THD will be low, and we require to choose generally the actually ratio of the triangular wave by modulating wave some kind of odd number, so that all the even harmonic will be eliminated. Now, there is another technique to increase the value of the PWM, value of the modulation index above 1. This is one application, it is called basically third harmonic injection, and actually third harmonic will be present only in the phase voltages. For this reason the line voltages will not have any third harmonic. Moreover, you do not connect actually midpoint and the neutral point, thus within that actually they will have a infinite impedance for the third harmonics. So, thus it will be trapped into the system and it will be not go out into the line voltages. And what is the bad advantages of it? So, this is actually the modulation waveform fundamental. With that you contaminate little amount of the third harmonics, and thus what will happen? Actually the ultimately resultant peak will become like this, but effectively this will be increased, and thus you will get little more modulation index, and also it will be in a linear region. That is, these are the two basic advantage, and this third harmonic will be restricted within the system, it will not go out in the line voltages. So, what are the advantages of it? So, at m equal to 1, modulating index equal to 1, so you are on the verge of the saturation. The value of the fundamental voltage, it is actually 0.5 VDC, and that is basically 4 pi d by 2 pi for the half bridge configuration. In this configuration we can show that this value can be increased to the 15 times more. So, maximum value can be increased to actually instead of the 0.785 to 0.907 by injecting the proper amount of the third harmonic. Now, there is a different amount of the can be injected for a different condition. So, one aspect that we require to reduce the THD, another aspect is that what is the maximum available value of the modulation index in a linear region. So, accordingly actually I left the student to calculate, let us say that actually that is the M fundamental plus actually k into 3f. So, value depending on the value of the k, we have a different kind of actually strategy. So, what you can do, actually you can think of, so you can take, students are requested to take two values, one is 1 by 6 and 1 by 4, and it check it out and what are the two conditions where actually the THD is minimum, and another case you will find that actually you will have a maximum utilization of the DC bus voltage. That can be achieved by actually simple calculations. While we are discussing this assignment, it will be this part and this assignment will be covered. So, we left it for this assignment to be solved. For this reason we are not discussing in details here. Okay. Now, what about over modulation? Over modulation is almost same. So, we do not get any benefit of the over modulation, and we are restricting to actually the saturation value of saturation value does not change. It is for Vd by 2 pi for the half bridge configuration. Now, we shall discuss about effect of the dead time. All the inverter, we shall go back to the circuit first, thereafter we will discuss. All the inverter required to give a dead time. So, what happen, otherwise there may be a dead short, because you know that most of this actually inverter made of IGBTs, IGBT have a current trail, thus it will take some time to turn off. For this reason, if any point of time both these switches are conducting, then there is a chance of the short circuit of the DC bus voltage, and DC bus voltage may collapse. And for this reason, we require to give little blanking. So, we say that because of the finite turn on time and turn off time of the switches, we wait and a blanking time Td, and this blanking time actually little bit increases and decreases the actually value of the load current. And also in addition, some kind of high frequency may appear into the system. We can see that what is actually blanking is a necessary evil. We require to provide blanking for the safety and the security, but due to that few phenomena will arise. Ultimately, your control circuit required to actually rectify those problems. See that this is actually sine triangle PWM, and ultimately this is the ideal transition, this point and this point. But what happened, you actually give a delay here, ultimately it will start in a conducting mode, little time difference of Td. But it depends, if you find that load current is positive, then you will find that actually when this transition occur, then it will be lossy. Why? Because we require to see that what are the mode of the conduction is going on. In positive half cycle, when current was flowing like this and it is going like this, then ultimately when it will off, there is a load, and thus default start conducting within the blanking time. So, for the positive, assuming that this is the direction of the current. So, similarly when actually D4 is conducting, when Q4 is conducting, so Q1 will come into the picture and there will be a loss into the system. Similarly, when voltage Vd is positive and current is negative, sometime it happens, most of the cases in the STATCOM application, then what happen, actually since current is negative, so D4 was conducting, then automatically actually D1 will conduct. So, thus you will find that there is a loss component in it, and actually system will be lossy. We will take care of the turn off and turn on accordingly, and we can make the system lossless by controlling the switching frequency. This is actually the lectures of the dead time. Thank you for your attention. We shall continue our discussions in next half an hour with space vector modulations and other and the hysteresis control, thereafter current mode PWM control. Thank you.